So in these two scenarios, an exponential growth model that has a fixed percent, the growth model will have a plus sign. The decay model will have a minus sign. All right. Trying to draw on top there. Also, we should point out that the rate is R equals whatever the percentage rate is as a decimal. Okay, so, and they say that here. It says no A is the initial amount. So the initial amount, A is the initial. Now, if you've already written it down and you read it, that's fine. I mean, just like for you guys to see it a second time. And R is the percentage increase or decrease written as a decimal. Okay. The quantity 1 plus R is the growth factor, and 1 minus R is the decay factor. So it still looks like y equals a times b raised to the x. But in this scenario, what they're doing is they're saying y equals a, and then 1 plus or minus r is like your b, and then they raise it to a t, right? So it's pretty much the same thing, right? This is the growth factor, b is the growth factor, and then this is the growth or decay factor depending on the value. So let's do one real quick, and then I'll real quick do another one. It says the value of a car can be approximated in this model. Y equals 25 times 0.85t, where t is the number of years since the car was purchased. So what does that mean? So this is this, and think in terms of b, is this, where does this live? Well, this is less than 1 but greater than 0, right? So what type of exponential model is this? Is this growth or decay? This is going to be a decay. And you guys don't know it, or maybe you do. This is a depreciation of a car after it's purchased. Now, it says in thousands, so what did they initially pay for the car? Well, A is the initial value, which is 25,000. That's what they initially paid for the car. Okay? But we'll just use this equation. So what you could do is just graph this, right? Because it doesn't really, you know, we're not really being asked to figure out anything in particular. They just, you know, what do you want to know about the car? Well, it'll depreciate over time. But let's pick a value. Let's say we want to know, let's estimate when it's going to be worth $8,000. Now there's a couple of ways you could do this. There isn't an easy way yet because I have to teach you the easy way. But probably the easiest way to do this is just to pull it up on Desmos. So what I can do is I can come over here, go to Desmos, and graph the original function, right? This function here. I could type in 25.85, right? Close my parentheses. Now you got to raise this to the x. And then the other thing I could do is I can figure out when that is going to be equal. Now remember, this is in this is in thousands, so I just got to say y equals 8, because y equals 8 represents 8,000, right? And already I have an intersection. That intersection is the value I'm looking for. Okay. So I'm going to scroll out a little bit. You could see that's how the value of the car depreciates over time. After the first year, it goes down a little, second year, third year, so on and so forth, okay? So let's take a screenshot of that. And what does that tell you? What information can you tell from that graph? What does that 7.00 or 7.011 represent? Well, that represents how many years it'll be until it's worth the $8,000, right? So let's put that in here. And I fired up the my other calculator, because what I want to do on my other calculator is I want to say 25 times 0.85 raised to the 7. Should be pretty close to 8. A little bit more than 8. See how that works? So that means it would be approximately 7 years for that value to be around $8,000. Now there's another way that you could do. Oops, I got to save it. I forgot on this program. You got to save it. 7. Oops. So it takes about 7 years for that car to drop down in its value to $8,000. That's it. And then the next section we'll show you how to do that algebraically. This is just a quick estimate using a calculator and stuff. Okay. Any questions on that one? All right. We're going to do one more. Does everybody have this written down, or do you need a minute to write it down? Does anybody need extra time to write this down? Can I go to the next screen? Does that mean no, don't go to the next screen? You got to write it down, or we're good? Okay. So we'll do one more example real quick. That was a decay. What do you think I'm going to do next? Now when it comes to these problems, these are real world examples. This is what this math is used for. So a lot of times when we teach you guys this stuff at first, we just kind of crank through the numbers and you guys are like, I don't understand what I need this for. Are you going to drive a car when you leave high school? Some cars depreciate better than others. So if you buy a car and one depreciates quickly and one depreciates, and you plan on trading that car in, you probably want to pick out one that doesn't depreciate as quickly. Just a little tip there. Alright, so I'll talk real slow while you guys kind of write this down. I'll go real slow so you guys can catch up. But basically this one is going to be a growth. It says in 2015 the world population was about 7.38 billion. During the next 5 years the world population increased about 1.09% each year. Write an exponential model that represents the population in billions. 2 years after 2015, then estimate the world population in 2020. So there's some important things. One is this is a growth model, right? Because the population of Earth is growing, right? So that means we would use this model, 1 plus r, right? A times 1 plus r raised to the t. Well, we need to know what a is. Remember, a is the initial value. What was the initial value? Well, that was 7.38. And when we say it like this, we're going to say in billions, right? We don't need to add all the zeros. It just makes the math a little harder. All right. 1 is 1. What about r? Do we know r? Yeah. They give us 1.09%, but how do I write that as a decimal? Isn't that 0.0109 as a decimal? You just move the decimal place over 2 spaces to the left. Do we know t? Yeah, it's 5 years. So my equation is y equals 7.38 times 1 plus 0.0109 raised to the 5. Does that make sense? Well, how do I find that answer? I just plug it in the calculator. That's it, really, truthfully. 7.38 times, oops, not 9. That changes the whole thing. Times 1 plus 0.0109 raised to the 5. And let me move my face out of the way. Let me take a picture of that. And a good rule of thumb, if they gave us 3 significant digits, in other words, they only did 3 digits here, which is 7.38, we would round this to 7.79, right? Now that was for 2020. You guys want to guess what the population is today? How would I change that for today, for 2024? What would I change? Remember, this model is in 2015 to predict 2020. What's the difference in those? 5 years. So how many years is it since 2020? 2024? 4. So you do the same thing, but you let t equal 9. So you would say, well, what's y equals 7.8 or 38 times 1.0109 raised to the 9? This gets scary. Just change that to a 9. 8 billion. How can we verify that? Just look it up. That's what it is right there. That's what we use math for. That's why you guys learn all this stuff. And by the way, the year isn't over, right? We're about halfway through the year. It's pretty close.